Hey everyone, welcome back, and today let's solve Leetcode problem 873, titled Length of Longest Fibonacci Subsequence. So a sequence x1, x2, and all the way till x to the n is a Fibonacci-like sequence if n is at least 3, meaning we have at least 3 elements in the sequence, and x sub I plus x sub I plus 1 is equal to x sub I plus 2 for all values I plus 2 that are less than or equal to or within bounds of n, which really means that all elements are the sum of the previous 2 elements for that sequence. And we're given a strictly increasing array of positive integers forming a sequence, and we want to return the length of the longest Fibonacci-like subsequence of the array that has these two properties, where it's at least 3 elements, and each element is the sum of its previous 2 values. And if one Fibonacci-like subsequence does not exist in the input array, then we simply have to return 0. And it's very important to note that we are actually given that it is a strictly increasing array. And a subsequence is derived from another sequence array by simply deleting any number of elements, also possibly none, from the array without actually changing the relative order of the remaining elements that we choose to keep. And for example, 3, 5, 8 would be a subsequence of 3, 4, 5, 6, 7, 8. 3 is on index 0, then we got 5, then we got 8. We're deleting 6, 7, and 4, and the relative order of 3, 5, and 8 in our subsequence still remains the same, where 3 is still before 5 and 5 is still before 8, just like how it is in the input array as a whole. But something like 4, 3, 8 would not be considered a subsequence because we're changing the relative order, whereas now 4 comes right after 3 when in reality, or rather 4 comes before 3, when in reality in the entire input array 4 would have to come after 3. So in example 1, we have our input array to be 1, 2, 3, 4, 5, 6, 7, 8, and in this case we actually have an output of 5. Keep in mind that is what 5 as an output really means. Basically, that tells us that for this input array, 5 is going to be the longest length of any Fibonacci-like subsequence of this input array. So the reason why this output is 5 is because the actual longest subsequence that has these two properties of being at least 3 elements, and this value being the sum of its previous 2 elements for all the input array, that's going to be 1, 2, 3, 5, 8. Notice how 1, 2, 3, 5, 8 is at least 3 elements, and in addition, each element is always the sum of the previous 2 elements for all elements in bounds with that property. Then what that really means is 3 is indeed 2 plus 1, 5 is indeed 2 plus 3, and 8 is indeed 5 plus 3. It all works out just like how the problem told us to, that this would be true for all I plus 2 that are less than or equal to 1, or that are less than or equal to n. And so it's also important to keep in mind the first 2 elements will not apply, because we need at least 2 elements to be the previous elements to even check if they are actually Fibonacci-like or not. Right? For example, we can't check if 2 is because 2 doesn't have 2 previous elements. We have to start from 3 and check, okay, 3 is 2 plus 1, 4 is 3 plus, or rather, 4 is, or rather, 5 is going to be 4 plus, or rather, sorry. We have to check in this. We can't actually check the first 2 elements where 2 is 1 plus nothing because we don't have 2 elements before 2. But we have to check whether 3, okay, is 2 plus 1. 5, okay, is 3 plus 2. 8, okay, is 5 plus 3. We can't check for this 1 or 2 because they don't have 2 elements previous to them. In example 2, we have our input array nums to be 1, 3, 7, 11, 12, 14, and 18. And also keep in mind this is, of course, strictly increasing like how the problem statement tells us. And in this case, we only have an output to be 3. Right, we can only at most form 3 elements that actually do form this Fibonacci-like subsequence. Now, we do actually have several different possible configurations. That would be 1, 11, 12. You could also take 3, 11, 14, or 7, 11, or 18. But it is actually proven that in this input array, there are not more than 3 elements that we can choose in one subsequence that are actually Fibonacci-like. And so 3 is the longest output. And to kind of verify these 3 valid potential subsequences, 12 is indeed 11 plus 1, 14 is indeed 3 plus 11, and 18 is indeed 7 plus 11. So for the constraints here, we see that the length of the array is always going to be within 3 and 1000, ensuring that we're not going to have like too large of an input array for the context of this problem's input constraints and algorithm that is exceeding 1000, and we're always guaranteed to have at least 3 elements to even have at least a chance of forming a valid, or rather a chance of having enough elements to form a valid Fibonacci-like subsequence. And we're also given that any value array at index I is going to be less than the element after it. It is strictly increasing, and that's always going to be within 10 to the 9th power and at least 1. So I will give you guys a few seconds. I'm going to just go over this problem in your head and think of a valid solution. And then I'll show you guys how I would optimally solve this problem in a few seconds. Okay, so what is one very important kind of observation or takeaway that we really need to make from this problem's constraints here, or rather from this problem's statement? Well, that is, we really have to consider and really leverage the definition of a Fibonacci-like subsequence and this main constraint here, very importantly, to actually build that longest or maximum length subsequence, right? And that is that, I'll also type it out and comment it out for you guys to really understand. A at any index I, let's just say A is a value, plus A at any index J, it always has to be equal to A at that index K. And the important thing to take away from this constraint, or this equation, is that I has to be less than J, and J has to be less than K, right? Basically, what this is saying is that these two elements have to always be equal, rather the sum of these two elements has to always be equal to this element, where these two elements come before this element. It is still in the relative order that's being maintained, and these two elements do actually have a sum of their next element, meaning they are actually Fibonacci-like values, right? And so basically, we have to actually find that longest subsequence that has this property for all the elements that we choose. That is, every single element with its previous two values for every single possible subsequence that we can potentially form that is actually Fibonacci-like, right? So how can we actually approach this efficiently and in a very, concise manner? Well, usually when you see subsequence problems, almost all the time, it is usually dynamic programming, and this problem is no exception. We are actually going to use dynamic programming to actually get or optimize how we choose our subsequences based on maximum length and if they are actually Fibonacci-like or not. And how can we actually do this very efficiently? Well, first of all, we can actually use a hash map or a dictionary data structure in Python to actually track these subsequences efficiently. And what I really mean by that is, instead of actually checking all the valid triplets of values which we could take, that would be kind of like the naive n cubed solution. Instead, we can actually use a hash map to actually keep track of the lengths of the Fibonacci-like subsequences ending at every single specific index and check from there, right? And for the dynamic programming approach, to actually use that DP approach with the hash map, we can actually maintain a dictionary DP, where DP at any index Ji, or any key Ji, is going to store the length of the longest Fibonacci subsequence that ends at those indices I and J. And of course, if array at any index K is the sum of the previous two elements, array at index I, array at index J, then of course we can actually extend the current subsequence to be one greater length, or another element to it. If that's not the case, though, we can simply start fresh or kind of initialize the sequence to be the length as 2 with the current two elements I and J, kind of like how we talked about in this equation as well. And you'll see how that works in the code as well, right? And basically, we have to just iterate through all the pairs IJ and update our DP dictionary based on all the K values that we see, if they are actually Fibonacci-like or not. So now let's go ahead and get into the code and really understand what this kind of high-level rundown of the solution really means. So let's first actually get our hash map, and I'll call it index because the whole point of this hash map is to actually get every single value's indices to check if they are actually maintaining the relative order for our subsequences that we actually check for and form to be Fibonacci-like. So this index is basically going to be a hash map, and I'm going to be using something called dictionary comprehension here in Python. It's going to be every single number, or num, mapped with its specific index I for every single value for every single index I and every single number num in the enumerate of the input array nums. Sorry, there should be array rather, right? And the enumerate basically keeps track of every single nums or element's indice as well in an input array or in a iterable, right? I would simply be every single index for every single value num that corresponds to that value. So we're basically mapping every single value in the input array with this corresponding index I in this hash map or in this index dictionary, right? Basically, we're storing the positions to actually allow us to quickly check if our sum for the current K value for the current subsequence, if it actually does exist in the array for that constant or big O of 1 lookup time, right? So now let's actually initialize our DP extra array or DP extra data structure. It's going to be initialized to a default dictionary, or in Python, simply just a default dict. And in this case, for our kind of default key value type, it's going to be a lambda with a default value of 2. Right? And this does look pretty obscure and kind of unique in syntax. Basically, what the entire point of this default dictionary really does, basically each key value each key j comma I would represent a subsequence that ends at those specific indices j and I, and we're actually setting the default length to be 2 using this lambda keyword here. And since we're really setting that default length to be 2 because any valid subsequence has to have at least 2 elements or 2 numbers, j and I, for it to even be valid and meet that Fibonacci-like subsequence criteria, right? So now let's actually get into our max length. This is going to be the result. This is what we're actually trying to store. It's going to be initialized to 0, right? This is our main result. This is what we're actually trying to find to actually solve this problem. It's going to keep track of the longest Fibonacci-like subsequence that we found so far, and in the entire input array eventually, once we actually process all the elements or all the indices. So now let's actually iterate through the input array for all values I and j and get their third value, k, to actually see if it's a sum of the previous 2 values and if it actually is a valid index. So basically the words this is going to work for I in the range of the length of our input array, and we're going to have nested loops here. So for every single value or index in the input array, we're going to loop through all the indices less than that value. So for j in the range of the current index I, right, effectively we're iterating through all the elements in the array with or using each index I. That's going to represent the end of our Fibonacci sequence, right? The current index I is going to represent the third value or the ending index of the Fibonacci sequence. It's going to have the index with the highest value. Not the array, or not the actual element at that index is going to have the highest value, not necessarily. Well, technically it will, but rather also the index is also going to have the highest value, right? And effectively, in this nested loop for j in the range of I, we're actually iterating for each index I, we're actually iterating over all the previous elements that are less than that index I. Basically, all the previous or smaller indices j that are less than I, which is going to represent the second to last or middle element of our sequence, right? And for every single value in this range, j and I, we'll get k to actually be something called the .get method in Python. It's very straightforward. Index.get the difference of the current 2 elements I and j. So array at I minus array at j. Basically, we're actually getting k to be the third or previous value of our input array, right? Basically, we're checking, okay, is the required k value, does it actually exist in the index, right? And that is array at index I minus array at index j, is it actually a valid number in the input array? Is it actually something that we can actually form an element from? If that's the case, well then array at index k has to be the first element at the current Fibonacci subsequence that ends at index ji, because we know that k, rather nums at k plus nums at I, has to equal array at j, right? Because j would be kind of like the last element that the previous 2 elements I and k have to sum up to, right? So once we actually get that, once we actually get the index, that is, as long as k is non-null, meaning it is actually a valid index. So in Python, there's actually a very straightforward way we can check this. If k is not none and it's actually less than j. What we're really doing here is if we actually do find a valid index, meaning it does actually exist, it's a valid index, and it is actually before the index j, to actually maintain that increasing in relative order sequence or order, right? Because very importantly, the problem tells us that it has to be a subsequence, meaning it actually maintains the relative order of all the elements. Now, we're guaranteed that I is the highest index value and value in general, and j is always going to be smaller than I, because we iterate for all j's that are in the range are smaller than I. And so as long as k is less than this second to last index j, we know that k has to also be less than I, meaning k would be the first element, j would be the second, and I would be the last element that nums at index I and nums at index j actually adds up to. K would be the first element that nums at index k plus nums at index j would actually add up to be equal to nums at index I, right? Basically, we iterate over each index I, and for each index I, we're iterating through all the previous elements at basically indices j, and we're iterating through, or rather, we're checking if the difference between the 2 elements, array at I, and array at j, if it actually does have a value, or rather index, that is less than j, meaning it is actually a valid relative order element that is less than j, meaning it comes before j, which also means it comes before I as well, because j comes before I as well, right? So if k actually exists and it is before j to maintain that increasing order, in that case, we can update our hash map, or our dictionary rather, dp at j at index I, to then be dp at k j plus 1. We're basically extending the sequence in this iteration by adding this current element k to the sequence, right? Basically, if we actually do find a valid sequence, meaning the k value is actually non-null and it is actually a valid sequence, we're simply updating dp at this index ji by actually extending the sequence from dp at kj and increasing its length accordingly, right? Because we're adding one element or extending the sequence's length by adding this current element to the current Fibonacci sequence that ends at index ji, right? That's what the key value really means in the context of this problem's hash mapping use case. And once we actually get that, now we want to actually dynamically update our maximum length. At each iteration, once we actually find every single new subsequence or extend every single new subsequence's length, we want to get the max length and update it. Either it can be the maximum of itself, meaning it hasn't changed, it's already bigger than the current one, or it would be dp at index ji. Either it could be what it was before, or it's going to be the length of the new sequence if it was longer than it was previously found, right? And again, what does dp at ji really mean? Basically, it's going to be all the length. It's going to be the length of the longest Fibonacci subsequence that ends at indices I and j, right? That's what the dp hash map really does. And effectively, once we actually process all the elements for all indices I and get all those valid Fibonacci-like subsequences and maximize their length accordingly for all of them, we have to return the maximum length. However, there is one last constraint that we have to actually address here. We can only return this maximum length if it is actually greater than or equal to 3. Because we know that the problem constraint tells us that a Fibonacci-like subsequence has to have at least 3 elements. And so if the maximum length was never actually greater than or equal to 3, we can't return it. We're only returning it if it is. However, if that was not the case, so else, if it's not greater than or equal to 3, we simply return 0. Right? So basically, if we didn't actually find a valid sequence that has a length greater than 3, we have to return 0. And if I were to submit this, this should actually be an accepted solution, and this should work. Okay, let's see what I did wrong here. Probably just a quick syntax error on my end. Feel free to just speed through this portion for I, num, and the numerator of the array. Default dictionary, max length for j in the range of I. Index.get array at I minus array at j. If k is non-null and k is less than j. Okay, yeah. So very, very straightforward error on my portion. I was talking about how dp at ji is actually the longest subsequence that ends at indices ij, and I swapped the order of them. This should be ji, not ij. Sorry about that, guys. And now this should be an accepted solution. Now this should actually work, unless I made a very simple syntax error again. Let's go ahead and check that. But as you can see, this does actually get accepted on Leetcode, and it is just about as efficient as you can get it to be. So let's actually get into how the code works as a whole very quickly here. Basically, we actually store the indices of all the elements for the quick lookup time. So actually check if we have valid indices or valid previous elements k for all indices in the input array. And what I mean by quick lookups is we actually check if it's an index in the index hash map, or a value that, we check if it's actually a value that exists in our hash map with its index being less than the second to last element, so it does actually monitor or maintain that relative order subsequence, right? And we're doing this in constant number of one time, using that or leveraging that constant lookup time from hash maps. And we basically iterate through each pair j comma I and check if a valid previous does actually exist, which would be k, where k would simply be the difference of the largest element nums at I minus nums at j, because we know nums at k plus nums at j has to be equal to nums at I. Right? And if we do actually find a subsequence, then we have to actually update the dp at index ji to extend the sequence by 1 and track the maximum length found in each iteration that we do that, and effectively return the result to be the maximum length that we found. Right? That's going to be allowing us to actually efficiently determine the length of the longest Fibonacci subsequence. So for the runtime complexity here, it is actually going to be a quadratic solution. It is big O of n squared, and would be the length of the number of elements of our input array. Why? Because we're actually having these nested loops here, as you can see here on lines 7 and 8, right? We actually do store, we do actually iterate through all the pairs ji and do actually perform constant time operations or lookups within those nested loops, so it is actually big O of n squared. And the memory or space complexity is also big O of n squared, because we are actually using this auxiliary memory here. We are actually using or storing values in the dp array for each pair j comma I in this dp and index hash map. More importantly, the bottleneck here would be the dp hash map that does actually store values for every single indices j and I. So if you guys enjoyed this solution and learned something new, please consider liking this video and subscribing to my channel. And without further ado, I will see you guys in the next video. Bye-bye.